the package you would like to import from that library, and then which class from that package you would like to use. For example, we could load up the Java library, and from there import the util package, short for utilities, and then from that utilities package, import the scanner class, a class which allows us to read information from the user. A package is simply a smaller set of functions and methods to help differentiate between the thousands of methods contained in a library, and a class is even more specialized than that. Now, if you don't know what specific classes you're going to want to pull methods from, you can use a star to import all classes within the package you'd like. However, it can be beneficial to be more specific and only import the classes you would like, as it helps with the efficiency of the program in the long run. For instance, in Python, the syntax to import a library is import followed by the library name. However, importing an entire library is more computationally taxing than importing specific functions from a library. Imagine you would only be using the factorial function from the Python math library. It would be a waste of computing power to import the entire library, and it would increase the load time for your program. For smaller programs, this isn't a big deal, but it really starts to add up when dealing with larger projects. Therefore, you would instead use from math import factorial, or the Java equivalent import java.math.factorial, and now have access to that one math command only. This limits the functions that you can use, however it saves programming runtime. If you decide you want to use another function that you hadn't planned for, you can always go back and import that too. Many times, if you try to use a function from a common package and you have not yet imported it, the IDE will prompt you to do so. If you're trying to figure out which libraries you want to import, think of the functions you're going to need in your program. Perform a simple Google search, and you will probably run into a package or library that already exists in your IDE that you can use. And if you can't, there are ways to download and import additional projects to fit your needs. But what if, after all that, you still can't find a library that contains the function you're looking for? Well, that's a perfect segue into what we're going to talk about next, which is the basic structure for writing your own functions.
So at this point, we've talked about both what functions are and how we can get some very useful functions by importing them through packages. But there are definitely going to be moments in your programming career where you're going to want to make your own functions because you want one to be made specifically to your program and code. Luckily, making your own functions is extremely simple. There are just some basic rules that I want to cover. Now, while we've previously used making functions as an example for other topics, such as the player stats function from a little bit ago, they were extremely abstract and didn't go into depth into what is needed for an actual function to operate. So right now we're going to be covering a skeletal system of everything that needs to be included in a function in order to get it to work. Now think back to the 4 different types of functions that we talked about previously. Functions that do and don't return values, and functions that both do and don't take in arguments. For creating your own functions, we're just going to have to go down the list and talk about how to approach creating each one of them, starting with the most basic of the bunch, one which takes in no arguments and returns no values. But before we start that, there are a few small things I want to note about function naming conventions. The variable naming conventions we talked about previously also translate over to function names. So you can't have 2-word functions, and you can't use special characters like periods or commas. Generally, you're going to want to follow the same camel case style which we talked about in the variables video, which is not capitalizing the first word, but capitalizing each word after that. Alright, so in general for making functions, each language differentiates on how you tell the computer that it's actually a function. In Java, you have to define the function's scope, which is something you don't really need to know unless you're going to become more invested in Java, but basically it tells the computer which parts of the code can use the function and which type can't. For this series, all of our functions that we make are going to be public. From there, you then determine which type of function it is. So in this case, since it won't be returning any variables, we'll just put void to signify this type of function will not be returning anything. Finally, you put the function name after those 2 identifiers, along with a set of parentheses after it like so. The parentheses are where your arguments would go if you were making a function that took in arguments. But since for our first type of function, we're not incorporating arguments into this function, let's just leave those blank. All of that is just for Java. Python, on the other hand, all you have to do is put the word def, short for define, and then the function name with a set of parentheses. So as you can see, each language is going to be a little bit different in how you make functions, but the main thing we want to remember is to always add parentheses. From there, we just type what we want our void function to do within the confines of the function and close it off, and we're done. In Java, the confines of the loop would be whatever is contained within the curly braces, and in Python it would be until you are no longer indented. At its core, this is the most primitive type of function we've made, something which takes in no arguments and returns no values, quite similar to the print_stats function from early on. Moving on to the next type of function, creating a void function that takes in arguments. Now this process is going to seem very similar to the previous, except for one small adjustment. Remember the parentheses that I mentioned earlier? Well, we put any variables we want the user to pass into the function into these parentheses, and then when we call that specific function, it will be required to have those variables passed into it. For example, in Java, let's make a function that takes in two numbers and prints out the product of those numbers. We start with the public void plus name of function setup again, since we won't be returning any values. And here comes a new part. Inside the parentheses, you define which type of variables you would like to pass in as arguments. In this case, an integer, and then a name for that variable. This name is what you will use to refer to the integer that the user passes in. For example, let's just call it num1. Then, if we want to add another argument, we simply add a comma in between the two, and we can make another integer variable, num2, to hold the second number. We could do this for however many variables we want to pass into the function. But for now, let's close off the parentheses and just print out the product of num1 and num2. As you can see, we refer to the two numbers that the user will input into the function as num1 and num2. Whatever numbers that the user passes into the function will be converted into num1 and num2. Now, whenever we want to call the multiply numbers function, we just have to make sure that we are putting two numbers in as arguments. In this case, the number 5 becomes num1 and the number 8 becomes num2. From there, we simply run the code and the number 40 is printed to the console. It's pretty important to note that you can also mix and match variables when making arguments. So you can have some function which takes in a car, an integer, and two strings all within one function. The last thing I want to mention about arguments is that when you call a function, you have to follow the variables you defined when making the function. So for our multiply numbers function, you couldn't put in a string and then an int. It has to be two integers because that's what the computer is expecting to be passed into the function. So now that we've gone over how to make functions that don't return variables, we have to cover those that do. And we'll start with ones that don't take in arguments. Now the main difference between defining functions that return variables and defining ones that do not is that in some cases you have to specify that you want this function to return an integer variable. This is most common in Java, where you would replace void with int to tell the computer that you want this function to give you something back to you in the form of an integer. This works the same as if you wanted to return a string, char, or even an array. You simply replace the word after public with whatever variable you want to be returned by that function. The most important thing to remember about making functions that return variables is that no matter what path your code takes, it must return a variable, no matter what. What does this mean? Well, let's say you had some string function in a game, and inside of it there was an if statement, where if the player's score was above 10, you returned a congratulatory message. This works fine if you printed the result of this function and the player's score is above 10, but if the player's score was less than 10, then you don't enter the if statement, and then you don't have something prepared to be returned to the user, and so the function is going to throw you an error. You have to have all your paths covered, which may seem simple, but if you're making a function with a switch statement in it containing high amounts of cases, then this can get out of hand very quickly. Something I like to do to make sure this doesn't happen is put a return statement at the bottom of a function with a string or an integer so unique that I'm able to tell that the code is not running properly and can fix it. Also, usually an IDE will let you know if there is a path in your code or in a function that does not return a variable when it should. The main point I'm trying to get across, however, is always cover your exits and make sure you have a return statement prepared for any case the user may throw at you. Another small thing to note is that you can't return one type of variable if you've already defined the function to return another type. For example, you can't return a string in an integer function or vice versa. The return statement must always match the type of function, no matter what. The final type of function is one that returns variables and also takes in arguments. And for these, all you need to do is combine what we've learned from the previous cases. First, you assign your arguments in between the parentheses, making sure that you have also defined what type of variable you want to return, and then ensure that no matter what path the code takes, that you're always returning that variable type. That concludes our discussion on functions. As you can probably tell, functions are an extremely vast subject area and require a little bit of practice to fully understand, which is why later on in this series we'll recommend some websites you can use to practice those more difficult topics.
Now, I'd like to switch gears a little bit and continue our discussion from earlier on arrays. Arrays, while useful, aren't the only way to store and manipulate information. In fact, there are a multitude of different ways to store data in computer science, including linked lists, stacks, queues, maps, trees, and many others too. Right now, though, I'd like to talk about two cool, wacky, and zany ways to store data that we haven't previously covered: array lists and dictionaries. But before we get into those, let's get a little review and reinforcement of arrays. As you may remember, arrays are basically lists of values that are stored together. When you initialize an array, you give it a size, and this size is fixed. You won't be able to increase the size of the array, so when you make an array, its length is final. To access the values in an array, you reference them using an index which starts at 0. What this means is that the first item of an array is not at position 1, it is at position 0, and its position is commonly referred to as its index location. So, to find the nth item in an array, you would refer to it as index location n-1. However, as the size of an array is fixed, you have to be careful to not reference a position that is beyond the total size of the array, or to append too many items to it, as this will return an error. We also have what are known as two-dimensional arrays, which is an array containing an array at each of its indexes. Or you could have an array containing arrays, containing arrays, containing arrays, containing arrays, depending on what you're trying to do. Multidimensional arrays can be useful in more advanced programs for organizing a wide volume of related values. If that's confusing at all, skip back to earlier for our full discussion on arrays. The timestamp will be in the description. Now that we've reviewed arrays, let's go over array lists. Array lists, or just lists in Python, can be thought of as a growing array. Earlier, we mentioned how you have to be careful to set an appropriate size of your array and to make sure that you only reference and append values such that you remain within the size. However, with array lists, this isn't a problem. After you initialize an array list, it instinctively has a size of 10. But if you append values such that the size of the array list goes beyond 10 elements, an array list will grow itself, meaning that the computer will allocate more memory to the array to increase its total size so that the new values can be appended. This is quite useful when you don't know the exact number of values that the array will need to store, or you want the ability to store more values to your heart's content, such as when you're making a database with an unknown amount of users that will sign up. There is a lot more to uncover when regarding array lists, but for this surface level series, that is all you pretty much need to know. So let's move on to dictionaries. Now when we're talking about dictionaries, we're not referencing that thick book you probably have lying around your house, which has thousands of definitions. In computer science, dictionaries are like arrays in that they store multiple values. However, their values are stored very differently. Rather than being referenced by their linear position within the dictionary, each value is tied to another value that is used to reference it, or its key. Because of this, we need to throw away all conceptions of dictionaries as a linear way of looking at data, since in actuality, it is much more fluid and interchanging. Basically, we say that each position in a dictionary holds a key-value pair. When referencing a value in a dictionary, you will use its unique key, and the dictionary will tell you the value that it is tied to. Think of it like this. Each time you add an item to your dictionary, your computer creates a handcrafted box to store the data, and also custom makes a jewel key, one of a kind, no other like it in the world. This way, there is only one key that goes to the box that stores a certain bit of information. Because each key must be unique, reusing a key in a dictionary will result in an error being thrown, because having two keys that are exactly the same would confuse the computer as to what box, or piece of information, that key leads to. However, you can store the same value in multiple key-value pairs, since the keys would all be different. Now, like I said, dictionaries are more fluid, making them easier to organize than arrays, as everything is set up in a more logical manner. That is to say, it is easier to find the value you are looking for when you are using keys rather than simply referencing their positions. Let me explain what I mean. Imagine you have a dictionary of prices at a store where the key is the name of the product and the value is the price of the item. Maybe apples cost $1, milk costs $2, and bread costs $3. You can see that in the dictionary, each key is the name of a product, and each value corresponds to the price of each product. So to find the price of bread, all you need to do is simply call the dictionary using the key bread. This makes it extremely easy to track values through your code since you're working with tangible values rather than numbers which don't mean anything to you. You can also manipulate dictionaries in many of the same ways you can manipulate arrays and array lists. You can iterate through a dictionary and perform many operations and comparisons on the values. If you want to find the product with the highest price, for example, you can iterate through the dictionary to find the value that is highest amongst the grocery store items. Arrays, array lists, and dictionaries are useful in their own right, as are the mass amounts of other ways to store data, and each boast certain advantages over one another. We already covered the basics of these three, but since there are so many, we don't have time to go in depth into each and every one of them. And so in order to help you grasp the basics of storing information, we're now going to talk about one of the most important functions needed to understand arrays, which are searching algorithms.
Now, just as there are many ways to store information in computer science, there are even more ways of searching through lists. Searching algorithms, at their core, are ways in which we can look through a list of values stored in an array, say a patient name list or a Hive score list, and find a particular piece of data. The goal of a searching algorithm is simply to give the algorithm a string or object you want it to find, and have it return the index of the array that contains that string or object as fast as possible. Now, while this may seem simple, lots of software runs on the backbone of being able to search through lists extremely quickly, making searching algorithms, and in particular efficient searching algorithms, an important topic to cover. Additionally, this is the main functionality that arrays are used for, and is the backbone of many of the methods used within array lists, as well as many other storage methods, so knowing them will take you a very long way. Typically, searching algorithms are used to return the index of a particular data point so that it can be used, modified, updated, or checked on. For example, if you're about to check into a hospital run on an array system for patients, the staff must search through your name in the database, and by returning the index of where your name is, they now have a quantifiable number that they can use to easily check you in, rent out prescriptions, schedule you for checkups, update your personal information, etc., without having to search through the list for your name every single time. You may think that there's little difference between searching algorithms, since computers nowadays can perform millions of calculations per second. But when you're a huge multi-billion-dollar corporation trying to find a certain data point in a list containing thousands or even millions of data points, small differences in efficiency are going to make or break the user experience. Even a 1% improvement in efficiency can mean big differences in the amount of time that a user is waiting for a simple task. Now, before we jump into different types of searching algorithms, we must discern between the two states that arrays or lists can be in, either sorted or unsorted. A sorted list of information is characterized by some sort of rankable value, whether that be a patient ID, credit card number, or even by alphabetical values like usernames or legal names. An unsorted list is just some random assortment of related information not sorted by any particular order or reason. Some searching algorithms only work for sorted lists, usually the more efficient ones, and some work for both sorted and unsorted lists. Although these are usually less efficient, if you end up pursuing computer science further, you'll have to deal with both sorted and unsorted lists, so it's good to know a common searching practice for both. Another thing to note is that we would determine the efficiency of searching algorithms based on both the worst case scenario and the average number of items it must search in order to find the index. We call this Big O notation, in which each searching algorithm has an equation which takes in the size of the array as an integer n and will output a worst case scenario efficiency value that we can use to compare with other searching algorithms. We can then also look at how long, on average, it takes to find an element in a list. Using these two methods allows us to easily compare how efficient two algorithms are. Alright, now that we've got some background on searching algorithms, let's hop right into it. The first type of search we'll be talking about is called a linear search, and you've honestly probably used this multiple times throughout your life. Every time you have to search for your name on a list of people, you probably follow the same pattern. You start at the top, check to see if the first name on the list is yours. If it is, great. If not, you move on to the next name on the list until either you find your name or you don't, in which case you leave. A linear search works in the same way. You start with the first element in the list, compare it to the value that you're trying to find, and if they're the same, you found your match and you return the index of that element. And if not, you move on to the next element in the list until you either find the thing you're searching for or you run out of lists to check. Pretty simple, right? This is because linear searches are pretty bad when it comes to efficiency, especially in the worst case scenario. If the item you're searching for in the list is the last element, you're going to have to check the entire list of items before you find the one you're searching for. On average, however, you're going to get it about halfway through the list. This makes the linear search O of n worst case scenario, since in the worst possible case it will take the entire length of the array, or n, to find the correct value. The linear search on average will return the correct index in O of n divided by 2, or halfway through the list. Now while the linear search isn't great, it can work with both sorted and unsorted lists, because of the fact that it will eventually cover every element in the list. The other search we're going to cover requires the list to be sorted, which may seem like a drawback, but having a sorted list allows you to use algorithms that are far more efficient than the linear search. So overall, the linear search is a good basic searching algorithm for if you have an unsorted list, but if your list is sorted, there are way more efficient options out there for you, such as the binary search, which we'll be talking about now. The binary search uses a recursive process to break the data in your list down into more and more manageable bytes, taking advantage of the fact that it's sorted in order to find the item you're looking for faster. This one is much harder to wrap your head around, so let's start with an example. Let's say you have a list of 10 names sorted alphabetically, like shown on the screen now, and you wanted to find your name within that list. In binary search, you would look for the middlemost name, in this case the one at the 4th index. Just a quick aside, since there's no true middle, since the list is 10 names long, the computer automatically uses the next one down as the middle value. Now, once you find your middle value, you first check to see if the name you're searching for at the index you've chosen is the name that you're looking for. If it is, you simply return that index. But 99% of the time, it's not going to be, including right now, so let's keep going. If the value at the middle name is not equal to the one you're searching for, you check to see if the value you're searching for comes before or after the middle index. For example, if you were looking for the name Brendan, and the value at the middle index was Carl, Brendan obviously comes before Carl alphabetically, and since we know that the list is sorted, what we can now do is ignore the entire bottom half of the list and just focus on the top, since we know that if Brendan is even in the list, it's going to be in that top half. Now, we simply treat the top half of the list as an entirely new entity and repeat the process over again. Again, we would find the middlemost element of this new list of names and again compare it to the name you're trying to find. If it's the name we're trying to find, we return that index, but if not, we compare it to see if it comes before or after the middle index. Going back to our example, let's say the middle index of this new list is AJ. Now we know that Brendan comes after AJ alphabetically, so what we can now do is ignore the top half of the list, since we know that if Brendan is in the list, it's not going to be in the top half of our list. Now, we again repeat this process again and again until we find the name we are looking for. So for our example, the middle index this time is Brendan, and that's what we're searching for, so finally we would return the index 2. In binary search, eventually the index we would compare to our search term will be the same, and once it is, we can return the index and move on. Now if we don't find it, which happens after we have eliminated